Okay, let's take a look at our ideal op amp. So we have our positive input, we have our negative input. They're connected by a very big resistor, Rn. For a perfect op amp, Rn's infinity, and if that's true, no current flows into or out of the inputs. We've got some sort of voltage source that allows us to put out a voltage, and of course any voltage source can be modeled as its Thevenin equivalent. There's some R out. For a perfect op amp, R out is 0. And there's something that causes the difference between the positive and negative input to be multiplied by some large gain and controlling what this voltage is. And we're going to make that be a little guy inside, a little gnome, who's going to look at the difference across Rn. And he's going to control R out. And he's pretty good. So that's where A comes in. If he sees any difference between these, he's going to try to adjust A out. So it's some large difference, large gain times this difference. Okay. How are we going to make this useful? Well, we have our golden rules. And they start out if there is negative feedback. Now, as you've already seen, in electronics, negative feedback is good and positive feedback in general is bad, although sometimes we'll use positive feedback. Negative feedback is good because it corrects for errors. We saw that in the emitter follower where VBE had a very strong temperature dependence, and of course as VBE changed, the collector currents changed, which caused our operating point to change. But when we put a resistor in RE to ground, between the emitter to ground, as the current change increased because the transistor got hotter and VBE decreased, when VBD decreased, the collector current increased. That causes more current through the emitter resistor. That causes the emitter voltage to go up, which decreased the collector current. And it kept the collector current relatively constant. That was an example of negative feedback. So in the op amp, negative feedback means that the output of the op amp can control the negative input of the op amp. If the output goes higher, the negative input goes higher. And of course, if the negative input goes higher, it causes the output to go lower. Similarly, if the output goes lower, it causes the negative input to go lower, which means that the positive input is at a higher voltage, the output goes higher. So in general, you can tell if there's negative feedback if you see some sort of connection between the output of the op amp and the negative input. Now, there's a few peculiar cases where whatever we put in the connection between the output and the input of the op amp can invert the signal. In that case, you'd have to connect to the positive input. Just keep that in mind, but for the most part, negative feedback means there's some connection between the output of the op amp and the negative input. And let's look at the most direct example of that. Let's just connect the output of the op amp to the negative input. Okay, let's apply some V in signal here, and here's V out. So the first rule, at least the first condition on the golden rule has been satisfied. We have negative feedback. Definitely the output of the op amp can affect the negative input of the op amp. So if that's true, the op amp will try to keep the negative input equal to the positive input. So you can think about it as this little guy in here, this gnome, is looking at the difference between these two, and if he sees that the negative input is too low, he increases this voltage, causing V out to go up. If he sees V minus is bigger than V plus, he decreases this voltage, causing V out to be lower. And his goal is to keep V plus and V minus exactly the same. We have a couple other rules that we have to keep in mind. V out is going to be less than or equal to, and I should add in the power supplies, VCC and VEE. So V out has to be less than VCC and greater than VEE. That's because there's nothing in the op amp except transistors, and we know that transistors, the output of an emitter can only go up to the collector value, actually can only go very close to the collector value, and also that the inputs also have to be between VCC and VEE. All right, let's see what that means for this circuit. Well, as long as V in is less than VCC and VEE, we know that this is going to work, and this little guy is going to try to keep V minus at the same voltage as V in, so that means that V out is going to be equal to V in, according to the golden rules. Well, if that's true, as long as V in is less than VCC and greater than VEE, V out will be less than VCC and greater than VEE, and V minus will be also. So this circuit should work and follow the golden rules as long as V in is between the power supply voltages. What good is it? Why do we care? We took V in and we got V in. Well, let's think about the input impedance of this circuit. How much current flows into the positive input node? Well, 0. Well, the input impedance is V in over I in plus, which is equal to V in over 0. Z in is equal to infinity. Well, that's a nice circuit, since we need the input impedance of the next stage of a circuit to be at least 10 times bigger than the output impedance of the previous stage. Infinity is pretty much 10 times bigger than everything except for infinity. Also, what's the output impedance of this circuit? Well, on first thought, you might think the output impedance is R out, which isn't an unreasonable thing. And if that's true and R out is 0, Z out is equal to 0. And that's really good too, because now we know that this has to drive a circuit that has an input impedance at least 10 times bigger than its output impedance. If its output impedance is 0, the next circuit just has to be 10 times bigger than 0, which is pretty much everything but 0. So this circuit, even though it doesn't do anything to the voltage, is called a buffer because it allows you to use any output impedance and connect it to any input impedance. So this is called a unity gain, sometimes follower, because the output follows the input, or sometimes it's called a unity gain buffer, because it buffers the signal by providing a high input impedance and a very low output impedance. This is a very useful circuit. Now, what if, well, actually, let's just go on and think about another way of looking at this circuit. So where do these golden rules come from? Why does this work? Well, let's take a look at what's actually going on. A perfect op amp, I should also write A equals infinity for a perfect op amp. So our rules for a perfect op amp: infinite input impedance, or 0 current flowing in or out of the input terminals, 0 output impedance, and infinite gain. And if that's true, V plus will equal to V minus if there's negative feedback. Let's go ahead and see what's actually going on. In real life, Rin isn't infinite, but the reality is with the op amps we use, it is so high, it's not likely to be something you have to worry about. We're talking about nanoamps or femtoamps of current flowing in the input, and that could be flowing either in or out. You don't know unless you look at the data sheet. It's dependent on how you build the op amp. But the currents are so small that unless the source impedance is in the megohms or tens of megohms, it's not going to cause you any trouble. A is not really infinite, as we already looked at in our quiz from the LF411. It's typically 200,000, but that's a pretty big number. And let's see why. So let's write our actual equations. So here, V plus, we're once again looking at this circuit, V plus is equal to V in. V minus is equal to V out because we've connected V out directly. We know that V out is also equal to A times V plus minus V minus. Okay, so now we can substitute do a little bit of algebra. We can say that V out is equal to A times, well, V plus is V in, minus V minus, well, that's just V out. We gather terms, and we end up with V out is equal to, well, V out times 1 plus A. We've got V out over here. We have minus AV out. Move it over here. We have V out plus AV out. And we can factor out the V out is equal to A times V in. And we want the gain of this circuit. Gain is V out over V in. And that's equal to A over 1 plus A. So up here, I claim that V out equals V in. By the way, that's V out is equal to 1 times V in. Our gain is 1. If this is a perfect op amp. But we can see that for a real-world op amp, that's A, the open loop gain, over 1 plus A. But for an LF411, that's 200,000 typically, over 200,000 plus 1. And if we take a look at what that is, correct, enter, enter, 1 plus, divide. Well, we better show some more. So we got 0.999995. Make sure I got enough digits there. 1, 2, 3, 4, 5 nines. So what we see is that in a real-world op amp, we don't get a perfect gain of 1, but we get something that's good to 1, 2, 3, 4, 5, 6, a few parts per million. And why is that true? It's because we have very high gain. You can see if we had lower gain, we'd have a larger error, a larger gain error. So what all that extra gain does is it reduces the error. It reduces the voltage required between the two inputs to get the output voltage we want. Now that gain actually does something else for us. Let's take a look. Now here's our ideal op amp with infinite input impedance and 0 output impedance. But the truth is, a real op amp has an output impedance on the order of 100 to 200 ohms. Now you might think that's bad, but as a former colleague of mine used to say, feedback fixes everything. So we looked at this and we saw that with a perfect op amp, the little gnome tried to keep these two voltages the same, and it did this by adjusting V out to be the same as V in. Now, suppose we add a resistor out here. Suppose I add an R load equal to 100 ohms. What do you think is going to happen? Now, your first instinct might say, well, we got 100 ohms here. We have 100 ohms here. We're going to get half the voltage there. That's true, but the half the voltage of what? Well, half the voltage of this internal voltage source. But the little gnome isn't looking at the voltage source. He's looking at the difference between the two inputs. And from his point of view, he adjusts this voltage until V out equals V in. So he's going to adjust this voltage, say V in equals 1 volt. He's going to adjust till V out equals 1 volt. And he's going to do that by making this 2 volts. Why? Because this impedance is going to drop some voltage. No currents flowing this way. But we have 10 milliamps flowing here. 1 volt over 100 ohms means we have 10 milliamps flowing here. Means we have a 1 volt drop across this resistor, but we don't care because all this little gnome, the feedback is doing, is adjusting the output so that these two are the same. So effectively, we have 0 output impedance. Why do we have 0 output impedance? Because we went from no current, when we had no load, to 10 milliamps, and the output didn't change at all, and that's the definition of 0 output impedance. Now, in real life, this doesn't have infinite input impedance. There has to be infinite gain. A is not infinity. It's 200,000 in the LF 411. So there's a little bit of voltage difference here. And that voltage difference has to be a little bigger if we need 2 volts here when there's current flowing rather than 1 volt. So there's a little bit of change in this voltage. But once again, this resistance is effectively divided by a number near A. And so even if it's 100 ohms, once we divide it by 200,000, we're in the milliohm range. So feedback causes this output impedance to effectively be 0. This is called a non-inverting configuration. Where is a nice color? And it's not inverting because the polarity of the output is the same as the polarity of the input. And you can usually tell it's a non-inverting configuration by the fact that the input is connected directly to the positive input of the op amp. But sometimes we want some gain. Suppose we wanted a circuit that had a gain of 10. How could we do that? Well, we're going to use a non-inverting configuration. I'm not showing the power supplies, but of course they have to be there. We want this voltage to be 10 times bigger than that voltage, but this voltage and that voltage have to be the same. So we are going to need to divide the output voltage by 10. So let's apply the golden rules. Is there negative feedback in this circuit? Sure there is. When this output goes up, the negative input goes up. Doesn't go up as much. If this goes up by 1 volt, this goes up by a 1/10 volt. But there's no question that the output can affect the negative input, so we definitely have negative feedback. If so, then V in equals V plus equals V minus. So we've got V minus here. But V minus is equal to V out over 10, because we have this divider here. And setting these two equal, we have V in is equal to V out over 10, or V out over V in equals 10, our gain. So this gives us a gain of 10 amplifier. And the output is the same polarity as the input, so it's a non-inverting And how can we get this circuit? Well, that's kind of easy. We know how to divide voltages. We use a voltage divider. And we need this to be a 9-to-1 ratio because we want 1/10 of the voltage to appear between the minus input and ground. We don't have these resistors exactly, but we have an 18K and a 2K. Now, what size should these resistors be? We could use 1.8K and 200 ohms. We could use 180K and 20K. We could use 1.8 megohms. How do we choose that? Well, since no current flows into the minus input of the amplifier, it really doesn't make a difference. We can think about this as an open circuit. Any 9-to-1 ratio will give us 1/10 of the output voltage here. But the reality is, if we make it too small, it's not going to work. And if we make it too big, it's not going to work. Why? Well, because the op amp isn't perfect. The op amp has a maximum amount of current it can put out. If you make these too small, the op amp can't provide enough current. If you make them too big, it turns out that I isn't exactly 0. It's pretty tiny, but if you make these resistors huge, then the amount of current that flows through these resistors starts to be close to the amount of tiny current that flows into the op amp. What's my recommendation? My recommendation is to choose resistors between 10K and a megohm. If you choose resistors in that range, you will not have to worry about the problems, the non-perfections of any of the op amps we use. So 18K and 2K is just fine. So, in this case, V out is equal to V in times, better give these some designations, R1 and R2. V minus is V out divided by the divider, which means that V out over V in is R1 plus R2 over R2. And oftentimes you'll see this written as 1 plus R1 over R2. You'll see it both ways. This is pretty common. The important thing to notice about this is that the minimum gain we can get out of this non-inverting circuit is 1. And that's when R2 is infinity or R1 is 0. And of course, when R1 is 0, that's just the buffer we showed you in the previous circuit. Notice that we can get any gain we want between 1 and a very large number. Now, you can't get any gain you want. You can't get a gain of 300,000 if the open loop gain of the op amp is only 200,000, because the gain comes from the open loop of the op amp. And the more gain you try to get in the closed loop, and I should mention we call this the closed loop gain. A is the open loop gain. That's just the op amp gain. Closed loop gain is what the circuit gain is. The closed loop gain should be significantly less than the open loop gain, because the open loop gain is what's making sure that our error is small. So if we want a gain of 200 and we don't have, and our open loop gain is 300, we're not going to have a lot of open loop gain left over to make the error small. And we won't get a very accurate gain of 200. On the other hand, if the open loop gain is 200,000, we don't have to worry as much. What the op amp does in the non-inverting configuration is it undoes whatever we put in the feedback. So here we divided by 10. The op amp has to multiply by 10. Why? Well, because this output has to be divided by 10 and give us the input. Well, that means that the op amp has to make the output 10 times bigger if we're going to divide by 10. And what that means is that we can put things other than just dividers in the feedback loop. And we'll see that in a couple parts of this where we start to put some strange stuff. The book talks about undoing the dog or hiding the dog. The dog is whatever we put in the feedback loop. And if this is f of v, this has to be f inverse of v. Why? Well, because when we multiply f inverse of v times f of v, we get v, and that's what the op amp wants to do. It wants to keep the minus input at the same voltage as the plus input. The other thing to notice about this circuit is since the input is connected directly to the positive input of the op amp and nothing else, and we know that for a perfect op amp no current flows in, the input impedance of this circuit is very high, approximately infinity, and the output impedance of almost any op amp circuit with feedback is very close to 0, because remember, the op amp doesn't care what the internal impedance of the op amp is. All it cares about is keeping V out at the correct voltage. So if we pull current out of here, even though it means there might be a voltage drop inside the op amp is just looking at this output, and if we pull current, it will adjust the internal voltage source so that this stays the same. So that gives us our non-inverting configuration. What we're going to do now is we're going to take quiz 2. Quiz 2 asks you about the non-inverting configuration. Then we're going to go into the lab and build 2 non-inverting circuits, the follower and the non-inverting amplifier. I should point out that the follower actually is just a version of the non-inverting amplifier where we made one of the resistors, in that case this one, 0, and therefore V out isn't divided at all. So when you're done with that, we'll come back, we'll take a look at the answers to quiz 2, and we'll talk about another configuration that gives us an inverted output. So a positive input gives us a negative output called the inverting configuration.